Hi everyone, we're gonna get started soon. If you can slowly get seated. Thanks. Good afternoon. Good lunch. Welcome to the second ZocMap talk of the semester, the first physics one. Today we have a talk in physics, and Advait, who's a second-year student in physics at ETH, is going to talk about the Large Hadron Collider. Please welcome him.
Yes, thank you very much. A pleasure to be here, and also wonderful to see so many familiar faces in the audience. Today I'll be talking about how the Large Hadron Collider works, what is studied there, and also give you a real-life example of how research is done there. So let's get right into it. I will talk about, first of all, the standard model of particle physics, because that's kind of what you're studying at the Large Hadron Collider. It's the model we have for modern-day particle physics, and it's been quite successful and rigorously tested. So I'm going to give a brief introduction into that, and then we're going to talk about the machine itself, the Large Hadron Collider, how it works, and how we can use it to test the standard model. And then we're going to do exactly that. We're going to test the standard model using the example of a three-prong tau lepton decay. Don't worry if you don't understand what those words mean. It'll make sense in a bit. All right, so let's start with kind of the fundamental question that everyone may have asked themselves when they were a kid. That's, what's the universe made of? And you kind of get the standard answer in high school that you have these atoms, which in Greek means indivisible. Kind of misleading, as we'll see. And these consist of a nucleus and electrons. And you kind of learn this in like basic middle school or high school. Then you go further in and you see that the nucleus isn't just a point, but it's also made of stuff, namely protons and neutrons. And for many, that's kind of the end of the line. But the rabbit hole does go deeper than that. And namely, protons and neutrons are made of particles called quarks. And then you can kind of ask yourself, like, how long do you want to keep playing this charade? So the answer is, there is an answer. So mathematically, you would be able to keep going indefinitely. But luckily, this is physics. So it does stop eventually due to something called the uncertainty principle. So after about 10 to the minus 32 meters, the notion of what exactly distance or size is breaks down. And so if there were anything smaller than that, you wouldn't be able to tell. So this is a pretty logical point to stop digging, exactly, length and size have no meaning. And so the particles that we're working with at this scale are so-called point particles because it doesn't make any sense to assign them any size or length. But this is quite an abstract concept. When you talk about atoms being indivisible, these are truly the indivisible building blocks of nature. Because dividing them would be meaningless. So this is what we're working with, but this is a very abstract concept. So you may ask yourself, how do you do any science with this? And so physicists came up with a model called the Standard Model of Particle Physics. This categorizes these particles, these point particles, into 12 so-called fermions, named after the American physicist Enrico Fermi. And these are what all matter is made of. But then you also want to describe the interactions that this matter undergoes with other matter. And so you have 5 bosons named after the Indian physicist Satyendra Bose. And these are the interactions of nature. So not only forces, but in general just interactions. And then you also have antiparticles, which are in addition to that, as you'll see on the next slide. And it's the best theory of modern-day particle physics. It's been tested rigorously. But it does have some flaws. So it's missing stuff like dark matter, which we can't explain yet. Also, gravity is not included in the standard model. And we also don't have unification. So there's this theory that all forces were unified at the beginning of the universe. We've unified some of the forces, but not all of them. So that's also a big gap in the standard model. And this is like your sort of periodic table view of the standard model. So you have all fermions and their antiparticles. And on the right side, you have all the interactions, bosons, and the Higgs boson, which was discovered in 2012. That was quite exciting. I just want to point out to pay special attention to the green particles. especially the tau and the anti-tau, because this will be very important in a bit. So the tau being the heaviest of the leptons, which is a category of fermions. And for the theorists among us, this is the standard model in its mathematical form. Enjoy. So now what? Now we have this cool theory that is very complicated, as we saw. But how do we do anything with it? How do we show that it works? And for this, we're going to test the standard model, and we conduct experiments to test certain properties of standard model interactions, being scattering amplitudes, masses, widths. The width is a statistical property, and so we can do experiments to kind of compare what the standard model tells us and what we're actually measuring. We can theorize new particles. That's always something physicists like to do, and then try to find them. Sometimes you find them, like you did in 2012, but most times you don't. Then you can just look for gaps or inconsistencies. If a certain interaction happens more often or less often than it should, there might be something behind that. And for this, we need a big fancy collider experiment to test our theories. Luckily, the Swiss government and a few other governments delivered, and they gave us the Large Hadron Collider. I'm going to pause to let that sink in. So this is the biggest particle accelerator in the world. Not only is it the biggest particle accelerator in the world, it's also the biggest machine in the world, period. It's in Geneva, Switzerland, and it has a circumference of 27 kilometers, and it was completed in 2008. Why did we discover the Higgs in 2012 and not sooner? Because it broke, and then they had to fix it. So that's why it was completed in 2008, but we only got the discovery in 2012. And how does it work? So this is kind of a schematic of the Large Hadron Collider. The big loop is the 27-kilometer ring I was talking about, and you accelerate particles around this ring, and you, using magnets, you make them collide at certain points, and we place experiments at those points. And you have a few smaller accelerators that kind of accelerate the particles before they enter the big ring. So the things that are being accelerated, as the name hadrons would suggest, is protons. Protons are hadrons, and you can obtain those by just ionizing hydrogen. So you ionize hydrogen, you accelerate them, and then you make them collide. How do you make something as small as a proton collide? You basically pack them in bunches of about 10 to the 11 protons, and then you shoot them towards each other and just hope that some of them collide. Most of them actually fly past each other, but a lot of them also collide. And then you have proton-proton collisions. And during these collisions, you have an energy of about 13 tera-electron volts. Electron volts is a unit of energy used in particle physics. And as Einstein's famous equation tells us, energy and mass are equivalent, as suggested by this formula E equals mc squared. And so this high energy that's produced during these collisions is converted into particles. So you get particles scattering, new particles are created, and then you somehow want to measure these particles. So for this, you build big detectors at the collision points, one of them being Atlas, which will be important later. And so at these collision points, you create particles that scatter out in all directions. And so you want to somehow measure the paths of these particles, measure their energies, and so on. And so you have different devices to do this. For energy and position, they're called calorimeters. The word calorie also suggests some form of energy. And you have about 1 billion collisions per second, so 1 gigahertz, and 13 tera-electron volts of energy per collision. So you have a lot of data to work with. When you're measuring these particles, you don't know exactly where the particle is flying because all you're seeing is energy signals in the detector. So you kind of have to reconstruct the path of the particle, and this is a very data-intensive process. And this is what a collision event looks like. So if the particles are colliding in the axis coming out of the screen, you have collision in all directions, and then your barrel-shaped detector can measure that, and you can do science with it. Let's have a closer look at Atlas. Reason will become clear shortly. So it's a cylindrical shaped all-round detector. That's why it's quite smart to look at Atlas, because it's not specifically made for one task, but it's made for all sorts of particles, all collisions. And it's 46 meters long, 25 meters in diameter, so it's not a small thing. It's the biggest detector, in fact, at CERN. And it's kind of like an onion, I would say. So you have your barrel, and you have layers as you go out. So you have the inner detector, which is very close to where the collisions are happening. And there you have a 2 Tesla magnetic field, which bends the trajectories of charged particles such that you can determine whether a particle that was created is charged or not using the Lorentz force. To measure these particles, you have so-called pixel and semiconductor detectors. So when a particle goes through the detector, you create a short electric pulse, which you can measure. And then by placing a lot of these layers next to each other, you can kind of reconstruct the path of the particle. Then you have, the muon chambers come at the end, but on the very outside, you have muon chambers, which are specifically only for muons because you can't measure them any other way. And these are so-called, these consist of many different mechanisms, which are listed here. But the main thing is that you want to measure different components of the muon's trajectory and then convert that into electrical signals so we can save it and do physics with it. Exactly. And then you have, in the middle, between the inner detector and the muon chambers, you have the electromagnetic and hadronic calorimeter. A calorimeter suggesting, again, something to do with energies. And the electromagnetic calorimeter is made of tungsten, copper, and lead layers. The only thing that these do is that because these are very dense materials, they cause the particle to decay very quickly and create so-called particle showers. So from one trajectory of a particle, you create a cascade of particles. And then those are easier to measure. The way you measure it is that between these layers you have argon, and then this gets ionized when a particle hits it, and then you get an electrical signal. And the HCal, the hadronic calorimeter, is almost exactly the same, but the only thing is that it's placed slightly more on the outside. So a light particle will decay early on, but a hadronic particle, which is slightly heavier, will make it through further. And so you can isolate whether a particle is lighter or heavier. Exactly, these are a few pictures of the Atlas detector. On the left you can see all the components I named, and there's also a few people on there for scale. So it's a very big machine. Exactly. And then once you generate this data that was converted into electrical signals, you have to somehow analyze it, which is not an easy task because 1 petabyte is produced per second, which is 1 million gigabytes. So you can't even imagine how much data that is. And because most of it is garbage, you have the so-called trigger system, the 3-level trigger system, which kind of determines whether or not a certain data point is to be saved. And it has 3 levels, the first one being a hardware-based trigger system. So if a certain event in the Atlas detector overcomes a certain energy level, then it is saved. If it's too low energy, no one cares about it and it's thrown away. So you enter with 1 gigahertz of data. Then there's a software-based analysis, which kind of looks at the properties of the event, determines whether it's interesting or not, and if it is, it makes it to the next level. And the last layer of the trigger system is the so-called reconstruction, where the path of the particle is quickly reconstructed, and then based on some parameters, you determine whether it's interesting or not. And this greatly reduces the amount of data we have to work with. And then this data is saved. They don't use normal SSDs or anything. They are saved on so-called tapes, which is very similar to the tapes that were used a long time ago. But these tapes are actually way, way more efficient than SSDs. So tapes are used. Exactly. Now I'm going to talk very quickly about a specific decay of a particle, namely the 3-prong tau decay of the tau lepton. The tau lepton being that particle I told you to pay attention to in the beginning. Exactly, it's the heaviest lepton. The leptons being electron, muon, and tauon. Tau lepton is also called tauon, by the way. It's very heavy, and it has a special property that it's heavy enough that it can decay into other leptons, but also decay into hadrons, which are heavier particles made of quarks. So this is why the tau lepton is so interesting, because we have a lot more decay modes, as indicated by this table here. So on the left you have the decay mode, on the right you have the probability of it happening. Sorry, the table's in German. So these hadronic decay modes, as you can see, are quite rare, and when something is rare in physics, that means it's more interesting. So this specific one is the one we're going to look at, which has a probability of about 9%, and it produces 3 pions, which are particles that are made of quarks, so they're not fundamental particles, but they are very common. So the tau lepton decays into these 3 pions of various charges, and also a tau neutrino, which is also a very light particle that is produced. So what happens fundamentally is that you have a tau and an anti-tau, so a tau and its antimatter partner. And the way these are produced are through 2 processes, which I will get into on the next slide, namely Julian process and gluon fusion. And so we're going to just call these tau 1 and tau 2 because it doesn't really matter which one's the particle, which one's the antiparticle. They're kind of, for our sake, it's kind of the same. So the first tau decays leptonically. That's into a muon or an electron, which is not that interesting, so we don't care. And the second one decays hadronically into a W boson, which is an interaction particle, which decays into a tau neutrino and into another particle called the A1 meson, which is unstable. So it decays into a rho meson and a pion, and the rho meson is also unstable, so it decays into a pion and an antipion. What exactly these particles are, it doesn't really matter. What only matters is that at the end, we can only measure these 3 pions that are produced, and we somehow need to prove that the rho and the A1 were momentarily produced during this decay, if we want to prove that this decay actually happens the way we think it happens. So this is what comes out at the end, 3 pions and a tau neutrino. And back in the days when you used to do particle physics with a cloud chamber, anytime 3 particles were produced, you would see sort of 3 lines coming out of the fog chamber. And so they named this the 3 prong, and the name stuck, even though you can't see it anymore. Exactly. So on the left, you have your Z boson, which decays into a tau lepton, and a tau that decays leptonically and a tau that decays hadronically, which I've indicated with subscript. And the leptonic decay is just into a muon, which is not that interesting. But the one on the bottom here is more interesting because you have a sort of you have many intermediate particles which are produced, and it's interesting to show that these exist. And the process using which you can produce these 2 taus are gluon fusion, where 2 gluons interact with each other and they produce a Z boson, or something called the Julian process, where 2 quarks interact with each other and produce 2 tau leptons. You don't need to know exactly what is happening here, but yeah, this is indicated by these diagrams, which are called Feynman diagrams. So now I'm going to get into what I actually did. So using data from LHC run 2, which is the run that they had in 2018, and approximately 100 gigabytes of data, what I did was I imposed cuts and filters to purify the data using a so-called Monte Carlo simulation. I'm going to get into what all of that means in a second. And what I wanted to do is show that this decay happens both for high energies, or specifically transverse momentum. That's what PT stands for. But for all sake and purposes, let's just think of it as energy. And just show that this happens. And also show that it happens for slightly lower energies, which is a bit more difficult because at low energies, things sort of melt together. So there, I had a bit more work, and I had to do the reconstruction myself. And the goal is to prove that these intermediate particles of the tau lepton decay are produced momentarily, hence proving that this decay exists and that the standard model is correct, at least for this decay. And this is a picture of me at the Atlas detector at CERN. Okay, so first of all, what are cuts and filters? I mentioned this previously. So whenever you have data, you want to plot it. And especially in Atlas, what happens is that for each collision, you have sort of a data frame of data, which in layman terms is just an Excel sheet, which basically tells you the index of the event of the collision, and then what particles are produced, what energy they have, what they're classified as. So you just have this sort of data frame, and you can plot various properties of this data frame. For example, if you want to plot the mass of 2 taus that are produced, and then how often they're produced, you can produce this plot. Only the black data points are actually what we measure. The colored ones are actually so-called background events, and that's why I'll get into the Monte Carlo simulation. So what you do is you use the standard model as we currently know it, and you create a simulation. So what would we measure if the standard model is correct the way we know it? What happens is that a lot of the time we think a certain event is 2 tau leptons being produced, when in fact it's actually something else, because obviously in the detector we're only measuring energies. So it's our job to kind of classify what's happening, and that goes wrong sometimes. So sometimes, for example, we'll produce 2 muons, but because muons have very similar properties to tauons, we'll think that they're tauons. And so the red part is just contributions from misidentified muons as tauons. And just like that, you have a lot of other interactions that are falsely identified as what we're looking for, which is the blue part. So these other events are called background, and the one that we're looking for is called signal. So our task is to maximize the blue contribution in the graph and minimize everything else. So if we plot them together, you can kind of see that what we measure is made up of not only actual tau events, but also a lot of other stuff that looks like tau events but is misidentified. We can make so-called cuts to remove the background, which is just sort of, in programming terms, it's a bunch of if statements. So we want to somehow isolate the signal that we're looking for. We can purify our selection to maximize the signal so that at the end, when we make physical interpretations out of this, we're actually looking at the right stuff. What you can do is that in this data frame that I mentioned, there's a column called decay mode. So for higher energies, what they've done is that they have automatically detected what decay is happening, and they've made it in this table. So the x-axis is called tau decay mode. It just tells you which decay is happening in this current tau event. And then on the y-axis, and then with the colors, you can see which decay is attributed to this. So you'll see that a lot of the time, the decay of the Z boson into 2 muons is identified into the first 2 decay modes. But the one that we're looking for, which is blue, is also in the first 2, but it's also present in 2, 3, 4, and 5, which is here. And here we don't have that much of the red decay. So since we want to get rid of the red decay, if we were to just throw all of this away, we would lose a lot of real signal, but we would also lose a lot of background, which is kind of a choice that we have to make. Are we going to throw away a lot of real signal, but have a very pure data set to work with? Or are we going to keep a lot of data, but then have a lot of noise that we don't want? So that's kind of a trade-off you have to make. And once you do that, you'll see that all of the red contributions disappear, and we have more beautiful looking graphs. And here, most of the contributions are from the blue, so Z to tau tau, which is what we want. But we also have the large yellow portion, which is QCD. These are just interactions that involve hadrons that are falsely identified as the decay we're looking for. And then you can plot various properties of this event. So that's the di-tau mass, which I also showed on the previous slide. And this is something called missing energy, missing transversal energy, which is sort of a concept where in a collision, you'll have a certain amount of energy that goes missing, which is due to neutrinos being produced and decaying away. So by determining the missing energy, you can kind of determine where the neutrino flew away. So we also have a distribution for that. And what we can now do is have a look at the graph and say, okay, if I want to only have the blue stuff, I can just throw everything else away. So if I just impose a strict if statement saying that the mass of the di-tau has to be between about 45 and 70, and I also say that the missing transversal energy has to be less than about 55, then I'll throw away a lot of unnecessary noise that I want to get rid of. So this is what I mean when I say a cut and a filter. So you're basically taking your data and you're removing everything that kind of disagrees with what you're looking at, which is a very common practice in physics. And this is what we do for high energies, so above 10 GeV. But now the struggle is when you want to do this for lower energies, because there you don't have these reconstruction algorithms that kind of determine what decay is happening, so you have to do everything yourself. And so, yeah, exactly. The small issue that we have is that the track reconstruction is not performed, and we're only working with energy signals in the detector, and we have to do everything ourselves. So the solution is you do it yourself. And what we were doing previously is we're looking for something called a jet, which in the Large Hadron Collider is when you have a beam of high-energy particles that fly out very quickly in one direction. And using this, you can reconstruct stuff for high energies. But at low energies, you don't have these jets, or they become inefficient. So instead of looking at these high-energy beams of particles, you look at the individual particle tracks themselves, which also exist at low energy. So if instead of looking for these jets, we look for these individual pion tracks, since we're looking for the three-prong decay, if we just look for these pion tracks, and then you loop over all possible triplets of these pairs, and perform cuts to kind of figure out which ones are the real ones, you can perform this reconstruction. So essentially what I'm saying is that instead of using these high energy beams, you look at the individual pion tracks and you loop over groups of 3 of them, and then you say, okay, are the charges as we wish that they, are the charges as they should be, are the masses as they should be, and then using that you can determine which triplets of particles actually belong together and which ones don't. And the result is that we can classify which 3 pion events belong together or were produced from the same collision. So what do I mean when I say we look at triplets of pions and determine which one fit together? Well, if I have a pion track, wait, let me draw this. If this is the Large Hadron Collider, or the Atlas detector seen from the side, this is the collision point, and I have a pion track that's going like this, and like this, then when I'm looping over them, I can just see like, oh, they don't have the same starting point. And so it's very, very unlikely that they were produced from the same collision. But if I use a different color, if instead I have something like this, then I can see that, oh, they were produced at the same collision point. And if I also measure their masses and make sure that they're not too high or too low, you can sort of say that this is something that works and this is something that doesn't work. And then when you're looping over all possible triplets of pions, you can save this and throw away this. So that's kind of the decision we have to make when we're doing the reconstruction ourselves. Yeah, so you do this using a nested 3 times for loop, which the programmers among us will know is not very efficient, which is why when you're working with Python, you kind of write a C++ script to do it for you, and then you kind of work between that, just for the computer scientists among us. And then what's also important is that since we're looking at events where 2 positive pions and 1 negative, or 2 negative and 1 positive is produced, you want to make sure that the sum of the charges is negative. So that, because if it were positive, that would mean that 3 positive ones are produced, and that's automatically not what we're looking for, so you can throw that away. So you can also look at the charges and figure out which one is legit and which one is not. All right, so if you do this and you plot the masses like I did previously, you get some wonderful plots, which I'll show you on the next slide. But before I do, I just wanted you to keep in mind that the mass, according to the standard model as we know it, of the A1 particle, which was kind of the intermediate particle produced in our decay, is about 1,260 megaelectron volts, or 1.2 GeV. And for the rho meson, it's 775 megaelectron volts, or 0.775 GeV. So when we do these plots for the mass, we should see a spike at these masses, because I think I can draw this one as well. It's very intuitive. If you have a particle here, let's say this is the A1 particle, and you're saying that this decays into a pion and a rho meson, then the sum of these masses has to be the mass of this particle. So, and then again, this decays further into a pion anti-pion pair, such that the charge is conserved. The masses of these two have to add up to the mass of this. So when I'm measuring these pions, I can look at what is the sum of the masses, and ideally it should be around this, and what is the sum of two oppositely charged pions, and this should ideally be the mass of this. So if I plot this in a graph like I showed, you should see a distribution that looks like this, where this is the mass of the A1 particle. You should see something like this, because most of the pions will have the mass of the A1, because they were produced from this A1. And you would see something similar for the rho 0 and these two particles. So this is how we would determine that these particles were momentarily existent in our decay. Yeah, just a small explanation. And now if we look at the graphs that are produced, you have this for transverse momentum higher than 10 GeV, and as you can see, you have a peak at almost exactly 1.2 GeV, which is the mass of the A1 particle, which would tell us that this particle was produced in these events, and so you have shown that the A1 does exist. And then similarly, if you do the same for low energies, the graphs are less beautiful because I had to do the reconstruction myself, and I was too lazy to use colors. But also here, you have a weak signal at about 1 GeV. The reason for this graph being less symmetric is because, as I mentioned, I had to do the reconstruction myself, and I'm not that experienced, so my cuts and filters that I chose, probably not the best. But you still do see a faint signal that some particle was produced there. And it's likely the A1, because the mass is, because 1 is approximately 1.2. And then if you look at, so this was, the first one was the mass of the 3 pions. So if you look at all of them together, they, as I mentioned, they should have added up to the mass of the A1 particle. But if you look at the mass of 2 pions, which would ideally add up to the mass of the rho, you can also see a peak at about 0.77 GeV, which means we have definitely found the rho particle here. You may be asking, what is this little bump over here? That's because when we're looking at these pions, you have to choose the 2 pions that are oppositely charged that were produced from the rho. But it's also possible that you choose the wrong 2 pions. So this is just a statistical bump that we have in the beginning from choosing the wrong one. But you have a very strong signal at 775 MeV, which means we have found the particles we were looking for. So in conclusion, the A1 and rho 0 meson are produced during this decay. And since this decay was predicted by the standard model, what we're essentially saying is that the standard model works, at least for this decay. So that's kind of a short overview of, first of all, what the standard model is, what the Large Hadron Collider is, and then how you can use the Large Hadron Collider to show that this decay predicted by the standard model exists. Thank you for listening. Can we do questions? Does anyone have any questions? Yes.
You mentioned earlier that there were multiple modes of decomposition of this particle. How did we understand that in this event, collision event, that it was this ion decomposition which was happening?
So you're asking in the beginning when we had these different decay modes. How we are able to identify. So basically, it's a mixture of many things. These days, they have a lot of machine learning models that, based on previous data, can determine whether an event is a certain decay or not. But also, if you just look at the masses, if you look at the angles that these particles are scattering at, you can easily determine. For high energies, it's very easy to determine which decay mode is currently happening. Yeah. Does that answer your question? Yes.
Thank you for the talk. It was very interesting. I have a concept question for myself. So initially we said how taus are leptons.
Yes.
And then later on in the 3-prong decay structure, you showed that there's a leptonic and a hadronic.
Yes.
If they're leptons, what does it mean for them to be leptonic and hadronic?
Good question. So what I meant by this subscript, wait, let me find the slide. Here. Yes. Do you mean this, where I said leptonic decay modes and hadronic decay modes? Basically, what we're saying is that 2 tau leptons are produced, an anti-tau and a tau, and then one of them decays into leptons, and the other one decays into hadrons. And so the one that decays into hadron, we're calling the hadronic decay mode, or the tau with the subscript had. And then the one that decays into leptons, we're calling the leptonic tau, which is indicated by the subscript lep. Yeah. Does that answer your question? Yeah. Any more questions? Then thank you for listening.
Thank you very much.
Yeah.
So we showed this graph of like